I find setting up tables for a lot of these things to be very helpful because you'll be dealing with a lot of parameters for a lot of these different joints. You're looking at joint rotation, joint moments, joint moment capacities versus demands, lots of different things like that. So tabulating this stuff in a comparative chart is, I think, very helpful for organization and keeping track of what joint is doing what. So the demand from this case will be these moments on each of those joints. So the demand on joint A will be this 1931 kip feet.
Did you get the capacity?
That came from our moment curvature analysis. Right, that's what we covered in the very beginning of the problem. We said we developed these moment curvature curves and these moment rotation curves. And we came up with the capacity of the section based on that. So we look at our moment curvature response. We got the ultimate and the yield curvatures for that. We then used an empirical equation for the plastic hinge length, because that's material dependent and detail dependent. So we used that equivalent plastic hinge length, that utilized plastic hinge length. We multiplied that by the difference between our ultimate and yield curvatures, and that gave us the plastic rotation capacity. Right? So that plastic rotation capacity had a plastic moment associated with it as well. So that plastic moment is what we're seeing here for the capacity. So it's important to note here that just because you have a moment in this joint does not mean that moment is subtracting from your initial capacity. In fact, in this case, the moments in member AB are actually adding to our capacity because they're in the opposite direction of our pushover analysis. So as we push this over, you'll notice that the moments between this and this flip directions. So as we were applying this lateral load for determining the sway, we saw as we push this over, the moments develop in this direction. But from our dead load, the moment is developing in that opposite direction. So these are actually going to be additive to our capacity. So these sum together. But on the other hand, for member CD, we see that this moment and this moment are in the same direction, which means the capacity here is being used up by the dead load. So instead of getting this additional capacity, like we did in member AB, member CD actually has moment being consumed just from the dead load. And so this will be subtracted. And you'll end up like this. So then for a unit lateral load, I just took this 73.63 kips, and I developed a scale factor like so. And then I just scaled these moments. Instead of by 1.104, I scaled them by whatever this turned out to be. Didn't have it written down. But that gives you the unit moments that develop associated with a 100 kip lateral load. So now we're scaling this back up because this is useful to us in terms of determining how much lateral force is going to be required to form our next plastic hinge. So if you come up with that scale factor and you multiply it by those unit moments, you end up with the following. And so now what you can do is you can look at this unit moment and divide it by the capacity of your joint. Because we're essentially going to be looking at this as instead of doing this really detailed nonlinear analysis, we're going to look at this as a sequence of linear elastic analyses that have nonlinear events occurring. And we can do that because we idealized this moment curvature analysis to have this very nice elastoplastic moment rotation response. So when you idealize that, you can do kind of the step way of working through the problem, because you're defining the nonlinear points as being these discrete events. Right? If you looked at the, say, the moment rotation curve, or even, let's say, the moment curvature curve for our sections, we had something like this. So because we only have two discrete points, we have, let's say, region 1 and region 2 for each joint. So you can do more complex analysis this way too. Don't get me wrong. You can do, let's say, instead of having elastoplastic, you want to have 3 or 4 different branches of your moment curvature curve. Sure, you can do that. It just makes the moment rotation response much more convoluted, and it adds a lot more work. And that's generally why design codes let you come up with this elastoplastic idealization, because it makes design much, much more feasible. Doing that more complex analysis with, let's say, 4 or 5 branches of your moment curvature curve and trying to get that plastic rotation response just becomes impractical. It's too involved from the analysis perspective. Especially if you're doing iterations on your design. You may spend weeks coming up with that pushover analysis. So if you do this, you end up with the following scale factors. So the reason we used a 100 kip lateral load is we can now very easily determine how much lateral force is required on this frame to develop a plastic hinge. So we just take this 17.86 scale factor, we multiply it by 100 kips, and we can come up with the amount of force required to form the first hinge. So because this is our first hinge, we don't need to worry about checking our plastic rotations yet, because no plastic rotation is started. But after this step, as we keep pushing this over, we want to make note that now this hinge at A, it can no longer take any more moment. This moment capacity now is 0 in terms of additional capacity, which means this joint now will start to rotate. And as it's rotating, it's going to be consuming part of its plastic rotation capacity. So for now, we don't have to check this, but as we develop more hinges, we need to keep that in mind as we go forward. So remember, the ultimate goal of this was to be able to determine the force and displacement capacities of our frame, because that's generally what we're going to be using for design. You want to be able to know what are the capacities of your system, so you can check those versus your demands. And so we have force now. The next step will be to determine what's the displacement of the frame associated with this force. So that's what we want to solve for next. I'm going to look at member AB, because this has nice defined boundary conditions. And for my unit load of 100 kips, I developed a lateral force there of 79.39 kips. So I took this column, I rotated it on its side, so it's looking like a cantilever beam now. And the moment associated with this was 1228. So that came from that scale factor times that we found that from that first sway analysis. Length of this is 30 feet. And I'm interested in delta. So I use double integration to solve for this. You can solve for it however you like. So now I've determined how much displacement the top of this frame has associated with that lateral load for a unit 100 kips. So I had that scale factor before, so I want to scale this now based on that scale factor as well, because this is for 100 kips of load, but I want how much displacement is associated with 1,786 kips of load. So I'm going to set up a table to keep track of what's going on with this frame, overall, big picture. So my first push is forming this first plastic hinge. And I came up with the unit displacement here, basically 0.05 feet. I multiply this by the scale factor. And up with a net displacement of 0.8618. And the total displacement of this will also be 0.8618. So as we go along, these two columns will be associated with one step. We're keeping track of the total displacement of the frame with this column here. And these three columns at the end, those are keeping track of the plastic rotation consumed in each of these steps. So in this case, we have no plastic rotation because we have just now formed our first hinge. So there's no plastic rotation consumed in any of those three joints. And what we can do then is we can start to develop the force displacement response of this frame. If you're interested in the stiffness of your structure in this case, for example, you're doing a dynamic analysis, you want, let's say, the natural period, and you need that stiffness to determine that, you can now look at, let's say, the slope of this force displacement curve and get the stiffness of this frame when it's in this state. So in this case, we're still in the elastic region between here and here. There's been no plastic or inelastic deformation occurring in any of our members. So K in this case would be our elastic stiffness. This would be 1786 kips. Over 0.8618 feet. I don't have that number written down, but you can easily work out that in local. What the stiffness in kips per foot would be for your frame. So we don't have too much time left. I don't want to jump into the next push and stop halfway. So So we'll pick this up next time.
Are you going to add to that list
Yes.
chart? Okay.
This will continue to develop with each subsequent push. So we'll do push 2, and then we'll determine how much displacement is associated with push 2. How much force do we get for push 2? And we'll keep getting increased totals in our force, increased totals in our displacement, and as we keep pushing, we'll start consuming plastic rotation capacity as well.